Hi all, welcome to iitiansgateclasses once again. So today we are starting with this problem of binary search tree again, that height of a node. So what is a height of a node? Given any node in the tree, the largest distance from that node to any leaf node, okay, that is called height of that node. For example, if you see here the distance from this node, this itself is leaf node, right? So its height is 0. Okay, its height is 0. Why? Because you cannot go down further and check the height. So its height is 0 here. Similarly, height is 0. Now for this node, the height is maximum distance. You can either go to left or right. Whichever is maximum, you can add +1 into it and calculate the height. Right? Why am I adding +1? Because if I calculate before this, the height is 0, right? So we are actually going one level above. So height for this node is actually 1 plus max of L, R. L means left subtree, R means right subtree. So here height is 1. Similarly, this itself is leaf node and its height is 0. And here if you see, the height is maximum of left, right +1. Here the left subtree have maximum height, left subtree have the maximum height, which is 1. On right side, we have height 0. And we will do +1, so height here is 2. Here itself is the leaf node. We cannot go down further. Okay, so here the height is 0. Similarly, here the height is 0. And for this one, the height is maximum of left and right. On the right side, we have height 2, and we will do +1. So here the height is 3. And similarly, here the height is 1. Here height is 4. 3, maximum of 3 and 1 is 3, right? And we will do +1. And here, before calculating here, we have to calculate all its children node also, right? So here height is 0, 0. It's 1 here. It's 2 here. And here its height is 5. So our function is basically to calculate height at any node, we have to do 1 plus maximum of height on the left side, left subtree, height on the right subtree. Whichever is maximum, we will do +1 to calculate the current node height. And height of a tree is actually height at root node. Height of a tree is actually height at the root node. Height is 5, right? We are that much high from our farthest leaf node. So right now, these two are the farthest leaf node. If you go here like this one is the farthest distance, right? So that is why our height is 5. Now we have to write down the program. You can go and check the previous program also. Okay, like this program. Counting number of nodes and counting height. You should know that how are we iterating the tree. Now we are calculating the height. Okay, so we will have a function height where we pass initially the root. Struct node star root. So this node is of root node. Okay. Now what we will do, if our root is null, what is our height? In case of null, we will return 0. Return 0, okay? We don't have to go further. Because from null, we cannot go anywhere. If root equal null, okay? Equal null. And if our root left equal null and root right equal null, it means that this is a leaf node. This condition says that this is a leaf node. And what is the height of the leaf node? It's 0 again. Okay, it's 0 again. Now in else part, it doesn't really matter whether you apply else or not, because if any of the above conditions satisfy, we are returning. Then in the else part, what we do, we calculate the left tree into left tree height. And left tree height is LH. We are denoting it with LH. Its height. We are calling the same function height. and we are passing left subtree node, or you can say left children node. Using this left children, this will act as a root for the left subtree. So we'll calculate the height of the left subtree in the LH. In LR, recursively we will call height root right. We'll recursively calculate height of the right subtree. Once both are calculated, we will return. So what is the height for this current node? In whichever node recursively we are at, what is the height? So its height is h equal to 1 plus maximum of LH comma LR. So this is the height of current node, and we will return h only, right? We'll return the h. Now recursively this program will be calculated for our root node, and we can calculate the height of our root node. Okay, I hope you understand this one. If you don't understand, try to go back to the yesterday's videos where I have written recursive function for many of the problems. Okay. Now let's see what is the number, or you can say level of any node. Level of any node. Here, the difference is that at leaf node, generally our level is not 0, it's 1 actually. At leaf node, generally our level is 1. So instead of starting from 0, we are starting from 1. Then what is our difference in the given program? The only difference is at leaf. Okay, at leaf node, you will do what you will do at leaf node. Generally, you will return, instead of 0, you return 1 here. That is the only difference. If you calculate the level instead of height, if you calculate level here, you will return 1 here. Okay, that is the only difference. Okay. So that is our program. So what if somebody asks you? What if somebody asks you that, okay, calculate number of nodes in leftmost path. In the leftmost path. It means that if we are given with something like this. So what is the number of nodes in the leftmost path? It's actually 2 nodes only. So if our tree will look like this, what is the number of nodes in leftmost path? We'll go left, left, left. It is this one, right? So if we want to calculate the number of nodes in the leftmost path for root, then there is no problem. If you want to calculate it for every node, then we again have to call the same function, right? So here it will return 1, it will return 1 here, it will return 1 here, right? And here in the leftmost path for this node, there is no leftmost path. So we'll count down only this node. Here we have 1 leftmost path, right? This one. So we have 2 nodes here. Okay, let me basically try to create a tree and make you understand. What if somebody asks you, what is the number of nodes at each node? We need to calculate the leftmost path number of nodes. At each node, we have to calculate this. Okay, we have to calculate the number of nodes in leftmost path. So let's start from this node. Here, how many nodes do we have in the leftmost path, including the current node? It's only 1, right? Here, how many nodes do we have? We have this children belongs to leftmost side, right? So it's 1 plus 1, 2 here. At this node, what is the leftmost path number of nodes? We have 1, 2, and 3, including the current node. Here we have 1 only. Here we have 1, 2, 3, and 4, right? Here we have 5. in the leftmost path. Here we have 1, here we have 1, here we have 1. Why 1 here? Because there is no leftmost path. There is nothing here on the left side. We have nodes on the right side, but we are not counting them. So in the leftmost path, we have only 1 node. Here also we don't have anything. That is why we have 1 here only. Now, how many nodes in the leftmost path of this node? 1 plus 1, 2 only. Now you see, we have so many nodes on the left subtree. In the left subtree, how many nodes do we have? 1, 2, 3. But we are calculating only by going on the left side. So we have 2 only here. Here we have 1, 1, and 2. Here we have 1 only. Here we have 1, 2, 1, 2, and 3 for this one. And for the root node, we have how many? 1, 2, 3, and 4. Okay, this is how you can calculate. And for the program level, so you will say, okay, leftmost path, LMP, something like this. I'm writing a random name here. And you have given struct node with the root node. And at each node, you are going to calculate the leftmost path, okay? Leftmost path. So let me change color. So if root equal null, what you will return? You will return 0. Okay. If root left equal null and root right equal null, it means that this is a leaf node, right? So we'll return 1 here in this case. 1. Why? Because even if there is a single node and there is no left or right node, it means it's a leaf node. Still, we count the current node in the leftmost path. Okay, we still count number of nodes as in the leftmost path. The current node we will count, right? Else, what we will do? We will say that okay, this is LH, number of nodes. On the LH side, we will calculate the number of nodes, right? LH side, we will calculate the number of nodes, which is LMP root left. And we have to calculate LMP for root right only also, but we don't have to save it because we don't concern about the right nodes. But for the right nodes, but here, for example, here for this node, to calculate the leftmost path number of nodes, which is this one, this one, this one, and this one, right? Total 4. 1, 2, 3, and 4. Still, you will going to call the function for this tree also, this tree also. So this is root, this is root right. But it will not contribute in the calculation of leftmost path number of nodes. Right subtree won't be contributed, won't contribute anything. Okay. So if it's not contributing in the number of nodes on the leftmost path, we'll calculate the function. We'll calculate the function, or we will call the function, but we don't have to save it anywhere, right? That's it. So you can return 1 plus LH. And if you want to save it somewhere in the array or somewhere, you can save like this is the number of nodes in the leftmost path. This is the program. Okay. Now let's see one more interesting problem, which is find if binary tree is a strict binary tree. Strict binary tree. Strict binary tree means either each node have exactly 2 children or it won't have any children. So this is a strict binary tree. This is a strict binary tree, right? But this is not a strict binary tree. Why? Because this node have only one children. Okay, so what is the program for this? Let me try to write the program for this one also. So we'll say that strict binary tree SBT, and we are passing struct node star root. So if root equal null, we will return. Okay, if there is no node. Okay, suppose this is our binary tree, there is no node here. There is no node, it's empty. Still, it is a strict binary tree, because if there is no node, there are no 1 or 2 children. Okay, so we'll return 1 here in that case. Okay, if so at the leaf level, we don't have any children, right? We don't have any children. We have 0 number of children, 0 number of children, 0 number of children at leaf. So this node can also be part of a strict binary tree, right? So root left equal null, and root right equal null. If this is the case, we will return 1. 1 indicates that it is a strict binary tree. Okay. But if this is the case where we are saying that, root left not equal to null, or root, okay, so we have 2 conditions here. We can say we have 2 conditions here. Root left not equal to null, and root right equal to null. Okay, one is this condition, okay. And let me write the outer basis in blue color. First one is this condition. We will say that or root left equal null, and root right not equal to null. It means these conditions are saying that we have only left children. This condition is saying that we have only left children, or we have only right children. If this is the case, then we will return 0 here. 0 indicates it is not a strict binary tree. It is not a strict binary tree. The current node is saying that I have exactly 1 child, either left or right. Then I will return 0. It is not a strict binary tree. So if any of the node returns 0, it means that the whole tree is a non-strict binary tree. So we will recursively call the function strict binary tree for left and right. Root left. So we will return if this condition is not satisfied. We are not at null. First one is this condition. We are not at the leaf node, which is this condition. And this condition is also not satisfied, where we have both the children are present, where we have both children present for the current node, right? If all these 3 conditions are not satisfied, then we have to call the strict binary tree for left subtree as well as the right subtree. So we'll say that strict binary tree and strict binary tree root left, root right, sorry. So the condition has to satisfy for left as well as right, and means both has to be true, right? Both has to be true. So let's construct a tree here in the previous tree. Okay, in the previous tree, This will return, this is a leaf node, right? This will return 0. This is a leaf node, this will return, sorry, not 0, this will return 1. Okay, see in the program, for leaf node, we are returning 1. So this will return 1, this will return 1. Now for this node, what we are saying that we have called the strict banditry for both the nodes, both the left and right subtree. So it should be 1 here and it should be 1 here. If any of them, you know the AND logic, right? In AND logic, 1 0 0 1 0 0 and 1 1. If this is our left subtree and this is our right subtree, then the result is, in case of this one 1 0, it will be 0. In case of 0 1, it will be 0. In case of 0 0, it will be 0. In case of 1 1, it will be 1 only. Okay, so this is our AND logic. AND logic. Okay, this AND logic represents the AND logic. Right. So for both, if both left and right are true, then we will have 1 here. And this is leaf node, so it will return 1 here. Both left and right are true, then we will have true here. This is leaf node, so we have true here. Both left and right are true, so we have true here. Here, these two are leaf nodes. Both left and right true, we will have 1 here. Now both left and right are like 1 1, we have 1 here. Similarly, here for this tree, let me actually make this tree a little bigger. Yeah, something like this. So now what will happen here? Let's compile this tree. This is a leaf node. For leaf node, we are returning 1, 1, 1, 1, and 1, and 1 here. Now, if both left and right are 1, we will return 1 here. Both left and right are 1, we will return 1 here. Both left and right are 1, we will return 1 here. Here, the left is 1. The left one is 1. But for this node, it will return 0. Why? Because it is satisfying this condition, this condition, this condition. It is saying that if left node is not null and right node is null, return 0 or this condition. This or will be checked once this condition is false. Okay, so I'm going to again diverting from the topic a bit, and I'm explaining one important concept: short circuit. So this is a programming concept where if in the if condition, or you can say in the for loop, you are right, for loop, right? Here you initialize it. After that, you provide a condition here, condition. Once this condition is satisfied, then only you will enter in the loop. So wherever you write condition in the programming languages, it follows short circuit logic. Short circuit logic. Okay, so what is short circuit logic? Short circuit logic says that if I have something like you can say logic 1 and logic 2. Now it will start looking from this direction. If logic 1 is false, or you can say 0, it will never go and check logic 2. Never. It will never check logic 2. Why? Because the whole condition depends upon the AND condition. If the first one is 0, the whole condition will always be 0. Will always be 0. Will always be 0. Okay, remember this. So this is short circuit. We are from this condition. If this is 1, then only we are going for the second condition. Similarly, for OR condition. OR condition. You know that what is OR condition? 1 0 0 1. Sorry, 1 0 0 0 0 1 1 1. Here for this one, this is 1 For this one, this is 0. For this one, this is 1. What is the meaning of OR condition? OR condition means if any of the input is true, if any of the logic is true, we will return true. So if we have logic, here like logic 1 or logic 2 or logic 3, any number of logic we have, if this one fails, then only it will check this condition. At least once one condition has to satisfy, right? If this one returns 1 or true, you can say, then we'll never execute these logics. We'll never execute in the programming language. We'll never execute these logics, right? So this is short circuit. If this is false, then only we will see for this logic. Similarly, going back to our problem, where we are saying that, where this condition, that root left is not equal to null and root right equal null. Okay. If this condition satisfied, it will never go and check this condition. This condition is saying that we have only left node. We don't have right node. We have only left node. We don't have right node. Okay, in the tree. So here we don't have any right node. So that is why it will return 0. Right? So see, whenever I am executing some program, I have to divert from the current program because sometimes the fundamental are necessary, right? Like short circuit logic. This is very important topic. You will see many like aptitude question, programming aptitude question on the short circuit logic in interviews. Okay, or you can say entrance of the interviews examination, some prerequisite examinations. So once this is 0, this is 1. If any of these two is 0, which we check here, right? Using this condition, both has to be 1. And condition says that both has to be 1. Now the left one is 0 and right one is 1. Then in that case, if left one is 0, it will never go and check this one. It will never go and check this one. Okay, remember this. So actually, this will never be executed. The return and the calling of the order. The calling order of the functions will be same. Remember this. The calling order will be same. Same means left, right, and root. First we will call left one, then we call right one, then we call root. Now here the left returns 0. Then in that case we will never execute and go and check this one. It won't be executed. Here if it's 0, this is 0. Now this is leaf node, we have 1 here. 1 0 0. And logic is there, right? And is there. 1 0 is 0. So this root is returning 0. It means that this tree is not strict binary tree. Okay. If you didn't understand the logic, you can go and execute this program. There is comparatively very smaller program. Let me write the smaller program also, right? Let me try to write the smaller version of that program. Strict binary tree, struct node, star, root, recursive function. Okay. And we are saying that if root equal null, return 1 here. If root left equal null and root right equal null, in that case return 1. In case of empty node, we are saying that okay, this is a strict binary tree because there is no node. In case of recursively, I'm saying this recursively, right? Similarly, in case of leaf node, you are saying that this leaf node don't have any children. So I said either 0 children or 2 children exactly. There cannot be 1 children. Okay. Then you say that if root left not equal to null and root right not equal to null, both are not equal to null. Both are not equal to null, right? Then I will check both the subtrees, left and right subtree. I will go down one level below. I will go one level below, right? Here, if it have both the children, I know it have both the children. It's satisfied for this one. But what if we need to check for the left and right also, right? What if this is the case? From here, we will propagate 0. From here, we will propagate 0 here. 0 here, till 0 here, then 0 here, then 0 here, right? We'll propagate 0 from this node because this node makes the whole tree strict, non-strict binary tree because it have exactly one child, right? So that is why our condition is true for this node, like this have exactly 2 children, but we need to check further. So to check further, we will recursively call return under this if condition. Under this if condition, we will return SBT root left and SBT root right. Okay. So whatever this function returns and this function return, we are applying AND logic on this, similar to the previous implementation. And this condition ends. If this is not satisfied, it means either this is null or this is null, because we have checked both the conditions. If both are null, we are saying that this is a leaf node and return 1. If both are not null, then in that case, we are going further one level down, else we will return 0. So you don't have to check this whole condition. This condition you don't have to check at all. So this is like a comparatively shorter implementation, where we have one condition here for the empty node, one condition here for the leaf node, one condition here if node have both the children, and one condition here which automatically states if we reach to this line of code, if we execute from this to this and we have reached to this line of code, it automatically indicates that our current node have exactly one child. Okay. Else we could have returned from here or here or here, right? So that is it for like a strict binary tree. Now let's see our next program, which is if 2 binary tree are equal or not. 2 binary tree are equal or not. Equal means both should have the same structure, both should have the same data sets. Okay, like this. Then the other tree should have the same structure and the same data. Like if we have 1, 2, 3, this is the data I'm writing. Here, inside this node, we have data 1, 2, 3, 4, 5, 6, 7, 8. Similarly, 1, 2, 3, 4, 5, 6, 7, 8. Both trees should be exactly same. Exactly same. You can pause the video and try to write down the program, because you have seen very compared to this program is quite easy. Compared to this program, you have seen very easy programs, right? So whenever we recursively call any function, we have to call for both the trees, right? We have to simulate both the trees. So how can we do that? We say that, okay, equal. I'm writing one equal function where we have struct node star root 1 and struct node, struct means struct, struct node star root 2. So we have root of both of the trees. Okay. Okay. Now what do we do? From here we will see that, okay, if 1 second, my earphone battery died actually. So I need to pause the view.
Okay, let's begin again. So what we are saying here is, let me choose some other color. We are saying that if both R1 equal null and R2 is also null, it means both the nodes. Recursively, we have reached to the nodes where both are null. Then we will return okay 1. 1 indicates that both the trees are not mirror image, sorry, both trees are equal. So again, if we say that if this is not true, not any of them is not null, we say that okay, if R1 equal null and R2 not equal to null, or R1 not equal to null and R2 equal null. This indicates that we have recursively reached to a node where for first tree we don't have a node and second tree we have a node and vice versa. It means both the trees are not equal, so we have to return 0. Okay, return 0. And we say that if R1 data equal R2 data also has to be equal, right? Then in that case, we'll go further down checking the subtrees, left and right subtree. Okay, so we will say that okay, the left logic, like you can say Boolean or bool, whatever is the data type, Boolean or bool, which saves true or false only. For the left tree, left logic, okay, for the left logic or left subtree logic, we'll call equal R1 left, comma R2 left. Okay, we are going in the same direction for both of the trees. And for the right logic, we are saying that equal R1 right and R2 right. Okay, we are going in the right direction or right children. Then we will go for in the right direction for both of the trees. So both of these right and left logic has to be true. So we'll return left logic and right logic. Okay. And this curly braces is for this if condition where we match the data. Now if data is not equal, else we'll return 0. Which indicates that trees are not equal. So write down this program and try to compile this program either in your C compiler, or you can say try to go through this program step by step. So this is our first condition where both the node are null. It means anyway node are equal, or you can say tree is equal, the subtree is equal because the subtree is null. Here this condition says that on the current node, recursively we have reached to a node where either left one, or either the first tree is not null or the right tree is not null and the other tree is null. Then in that case we have to return 0. So the third condition says that data is equal. So we have to check the children, left and right children. And on the left and right children also, the tree should be equal. Okay. And if data is not equal, so this condition says that data is not equal, different. Now we will say some mirror image function. So what is mirror image? Let me try to write down a tree A, B, C, D, E, F and G. Now suppose we have a mirror here. We have a mirror here, right? So this mirror flips this tree, right? So if we flip A will remain same. If we flip this level, so C will come here, B will come here. So this is the mirror image, right? And G will come here, F will come here, E will come here, and D will come here. So this is D. This is the mirror image, right? Mirror image of this tree. Okay, so try to assume that this is the tree facing this part is facing to the mirror, and this is the mirror. So tree will flip. The C will come here, B will come here. So this is the mirror image. So we need to write down the program to construct the mirror image of a given tree. Try to follow up the program, right? So we are given with the root. I'm not giving the data type. It's struct node only. Struct node star root. So if root is null, root equal null, just return null. Okay, because for the null tree we are having null option only. We don't have any option. So if root left equal null and root, so again this is for leaf node, and on the leaf node you don't have any further subtree, so you don't have to do any processing. Right equal null, so we are not doing any processing, we are just returning root. But if this is node leaf node, then in that case what you will see, you will save a temporary pointer struct node star temporary pointer t temp or temp, a temporary pointer temp, where it will save the left subtree, okay. And on the left subtree of root, we are saving the right one, and right one we have to go further down, right? So recursively we have to flip the right subtree also, right? We have to flip right subtree. So what we are doing, what is our intention? Our intention is like this. Do one thing, okay? So this is the left pointer of root, left pointer, right pointer. So the left pointer is pointing down to this one, the right pointer is pointing down to this one. Now, 1 second. Now, do one thing. The right will point down to this one, the left will point down to this one. And recursively, we have to call the same function for this tree also. Okay, this should point down to this left we need to break, and this should point down to this one, and this should point down to this one, right? So we will call recursively, we call this function mirror image, and here we pass root right. So on the left side we will have the right pointer. On the root left we will have the right pointer, and this right subtree is also mirrored, right? Subtree is also mirrored, right? Similarly, on the root left right, we will call mirror function. Now we cannot pass root left because it's already set to root right mirror image. Root right subtree mirror image. Root right subtree mirror image. Okay, I will explain using the same example. I will explain what we are doing here. So this is already set to required pointer. So you cannot use this one. That is why we have used this temporary. So we have to pass stamp here. right? We have to pass temp here. And we have to return root. See what we are doing. Let's go back here. Here we have to develop the mirror image, this image. So let's talk about only this part. Here we said that on the left one, save this left one in the temporary pointer. So we have a temporary pointer which is pointing to this one. And we saved on the left side, we saved the mirror image of this one, the mirror image of this one. What is the mirror image of this one? Let's see what is the mirror image of this one. This is the mirror image. So it's CFG, right? So we'll flip it. So it's CGF. It's C here, G here, and F here. Previously it was C, F, G. So we have calculated the mirror image, and on the left side we pointed down CGF. So this left pointer is pointing down to this one. Now this right is also pointing down to this one right now. So we need to build this relation again such that this right will point down to this subtree, the mirror image of this subtree, the mirror image of this subtree. Okay, the mirror image of this subtree is BDE. Right now it's BDE. What is the mirror image of this one? It's B, E, and D, right? E and D. B, E, and D. See right now. So once these are the arrows now, this is the right arrow, this is left arrow. So we can also write down it in this language, this right, okay? This right is pointing down to the mirror image of this subtree, which is BED. Okay, this right is pointing down to BED. Left is pointing down to CGF, okay, CGF. That is why we have to call mirror on the subtree. We had to call the mirror image of this subtree. Okay, write down this program and try to understand it. Now our next topic is binary search tree. Binary search tree, which we will see tomorrow. Here, binary search tree is actually a binary tree with one condition, that for any node, the left subtree will have lesser value, and right subtree have greater value for any node. Okay, so we can write it like we have 80 here, then we have something like 20 here, 10 here, and for 20 we have a smaller value here and larger value here. So here we have something like you can say 50, and for 50 we cannot have greater value on the left side, so we have 40 here, and for 50 we have greater value here, so we'll have 60 here, something like this. Okay, and here we have like 120. Here we have smaller value compared to 120. Here we have greater value compared to 120. So you have to look for each node. At each node on the left subtree, in the whole left subtree, we have smaller value compared to this node. And in the whole right subtree, we have greater value. For example, here we have all the values on the right subtree we have, which will be greater than 20. Why the binary tree is like this? Because it makes searching easier, right? Each time you prune means you ignore, or you can say you ignore the one half. For example, if you want to search 50 in this binary tree, you will check the root. Okay, 50 is smaller than this one. So you will never go on the right side. You will go on this side of the tree. Then 50 is greater than 20. So you will never go on the left side. You will go on the right side of the tree. That is why searching is easier. Each time you are choosing one out of two. And binary search algorithm will take order of log n, similar to binary search, right? We have seen the binary search algorithm where we have a sorted array, and in array, each time we avoid the half, either this half or this half. Similar to this one, either we avoid the left subtree or right subtree. Because the property of binary tree is as such that the current node is basically greater than all the left nodes, all the left subtree nodes, and the current node is smaller than all the right subtree nodes. That is why the searching is easy. It's order of log n. Only in condition where our tree is balanced. Balance means it should not be like this. If you have all the nodes and these are like this, okay, 100 here, 200 here, 300 here. Okay, we have only right tree, 400 here, 500 here. How many nodes do we have? 500 nodes. Sorry, 5 nodes. And to search 500 in the binary tree, what is the effort? We have to go through all the nodes. So it's skewed. So in case of skewed tree, either right skewed or left skewed. Skewed binary tree, the searching is order of n because we have to go through all the nodes to reach to the destined node. Okay, so we will see more programs on the binary search tree and application of binary search tree tomorrow. Thank you all for tomorrow in the next lecture. Okay, thank you all for joining.